Welcome to BKW Physics. I'm Mr. McConnelly, and today we're going to jump into circular motion. It's also been called periodic motion. And there's three main areas we're going to touch on. We're going to touch on the velocity of things moving in a circle, the acceleration of things moving in a circle, which might sound like a, I'll get back to that, and then the force when something's moving in a circle. Let's start with the velocity, that's easiest. If you have something moving in a circle, by the way, if you try to draw a halfway decent circle on your page, if you start with your pencil at one point and then never look away from that point as you draw the circle, you get a much better circle. Just a little bit. So anyway, you got some object, say it's a, say this is a top view and you got a string with a rock on the end of the string, and you're spinning it over your head or whatever. This object's going around and around. And if we look at this object at the point I've drawn it right now, if that string were to break, where does the rock go? Does it go out, or out, or out, or out? Okay. It actually goes like this. It goes tangent. It goes tangent to the circle at the point that the string breaks. It will continue in a straight line tangent from where it was released. Now, if you were trying to figure out how fast it's going around, say you're spinning it at a constant speed, how do you figure out how fast? It's really not that hard. All I want to do is say, okay, what's my distance and what's my time? Because if you're going at a constant speed. So what's the distance of around a circle? Circumference, 2 pi r. And since it's periodic motion or circular motion, in terms of t, we usually use the letter tau. Tau meaning the time it takes for one complete cycle, like we did with pendulums. Tau. So if you want the velocity, it's 2 pi r over tau. Now you won't find this in your reference table, unfortunately. But most people don't have a real hard time remembering it because they're like, okay, it's just how far around the circle divided by how much time it took. That's like distance divided by time. You will find, obviously this is our first equation, you will find that in the reference table, but that you won't really find. Alright, so besides things going tangent, let's hop over to acceleration. This one gets dicey for some people because you're like, well, you just told me a second ago it's going at a constant speed. So if it's going at a constant speed, how can it be accelerating? Question mark in your voice. Anyone have a thought on how you can be accelerating when you're going at constant speed? Your acceleration is not 0. Well, the way you're thinking of it is probably 0. Because, take this picture, back to this picture. If the rock is right there, let's say this string doesn't break now. Right now the velocity is pointing this way, right? A moment later, the rock will be over here, and the velocity will be pointing this way. A moment later, the rock will be over here, and the velocity will be pointing this way. So what are you noticing about the velocity? It's, say the word? Changing. What is the definition of acceleration? Changing velocity. So since you are changing your velocity, now the part that gets sticky for some people is you've always thought it meant that you had to be changing the number, the actual speed. Some of you thought like, oh, you got to be going 10, and then going 12, and then going 14. That would be changing your speed. You thought it had to be that way, but it can also be, since velocity is a vector, it can also be changing the direction that the velocity is pointing. So this velocity could be 20, and then 20, and then 20, and you are accelerating because you're pointing in a different direction. Alright, so we've moved past that. You get how this can be an acceleration, hopefully. Well, how do you figure it out? Well, if you want to know the acceleration of something that's moving in a circle, it's the velocity squared over the radius. Now this is in your reference table. And the little c for centripetal. Centripetal. And that word centripetal means center seeking. I point this out to you because there's another word that sounds a lot like it, centrifugal. Centrifugal is not the same word. Centrifugal is outward seeking. We're not talking about that. And that one's not a real physics term anyway. Okay? The real physics term is centripetal, and centripetal means towards the middle. So you're like, wait a second. So first you tell me that you're accelerating although you're going the same speed, but I think we worked through that one. I think you're all right with that one. Now I'm telling you the acceleration is towards the center, but I just drew you the picture that said if the string breaks, you're going to go flying outward. What's going on? Let's draw the picture one more time. So, if you got a circle here, and this object, whatever this object is, let's say it's a block of wood now being spun on a string. The block of wood is spinning around this way. How can I possibly say that the acceleration is center seeking? Well, think of it this way. What is making the block? Because right now the velocity is like this, and the velocity is like this, just like we drew before. What is making the velocity change direction this way? What is this string really doing for you? What'd you say?
I said anchor.
It's anchoring. So you can think of this as like a fixed anchor. And so it's actually kind of pulling that way, isn't it? Yeah. Well, since you are pulling this way, pulling this way, pulling this way, pulling this way, can you see that the acceleration is actually pulling towards the center? Now once the string breaks, all bets are off. Then the thing just goes straight because of the idea of inertia and momentum. An object in motion will continue in motion, right? So once the string breaks, it's going straight. But until it breaks, if that string is still good and strong, it's going to keep pulling or accelerating you towards the center of the circle. So the acceleration of an object moving in a circle is pointed towards the middle. You better highlight that concept. The acceleration of something going in a circle is pointed towards the middle. So it's a center-seeking acceleration. V is your velocity, which would be, of course, in meters per second, and R is the radius of the circle, which would be in meters. Okay? So, think of it, just for a moment before we move on to the next thing, think of it like you're driving a car. You're driving along the car, you take a corner real fast. Whoa, and you go around the corner. Which way does your body want to fly? Outward. You know what I mean? Like, if you take a left hand, we're driving, we take a left-hand corner, my body wants to go to the right. Because my body wants to keep going in a straight line because of inertia. But what is it that is causing me to accelerate to the left? Yeah, the seatbelt, the tires on the road, all the friction, you know, everything like that's keeping the car on the road is allowing you to go left. So you accelerate to the left, but you feel like you want to go to the right. Last thing, force. So, we know F equals ma. We've known it, we took a test on it, we're good. All I want to change this time is add the fact that this, we're talking about centripetal. So when you go and find this acceleration, you're really using this equation from over here. That's all that changes. It's still the same. And what did we learn back to the bicycle demo earlier in the year? What did we learn about the direction of acceleration compared to the direction of the force?
It accelerates in the force.
These have to be the same direction, and that's still true. So, back to my picture, one step over here. If I'm accelerating towards the center of the circle, what direction is my force? And I think we kind of already said that when we were talking about it. we said there's got to be something pulling, and the definition of a pull is a force. So, boom, 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 boom. Velocity, acceleration, and force. Now I want to quickly move over to a demo here. So can you kind of spin that thing so it points to the back corner?
Gotta take
Catch me right here first, okay? I just want you to notice that there's some water in the bucket.
Gotcha.
Put this chair down so it's out of the way. Is that good?
Yep, Chris, your head's in the way.
That's better, right?
Yes, sir.
See me?
Yes, I can.
Alright, so I take this bucket of water, and I can do this. If I slow it down, it's still a little drop, but not too bad. So how is that possible? Let's go back to the picture. Which direction is the acceleration? Towards the center. Which way does the water want to keep moving though?
Out.
The water wants to move out because of inertia, but the acceleration, what is providing the force for the acceleration? My arm, basically, right? I'm pulling this thing around in a circle, and the bucket is accelerating the water towards the center, and the water wants to keep going out, so it just stays stuck to the bottom of the bucket, and it doesn't fall out. For today, physics.